All right, let's dive right in. All over the world, in countless factories and plants, you've got these huge sealed tanks, and they're holding everything from chemicals to, well, even milk. But think about it. How do they actually know what's inside without sending some poor soul up a ladder to peek in all the time? Well, that's exactly what we're going to unpack today. It seems like a simple question, right? I mean, just picture a giant sealed can. You can't see inside. Is it full? Is it half empty? Is it about to run out? Now, in industry, getting that answer wrong, oh boy, that can mean massive spills, costly shutdowns, or tons of ruined products. The solution, it turns out, is some seriously clever tech called level sensors. So here's the game plan for today. First, we're going to talk about why this automation is so critical. Then we'll break down the two main flavors of sensors you'll find out there. After that, we'll get into the nitty-gritty of the specialists, the ones that detect just a single point. Then we'll check out the sensors that measure the entire range. And we'll wrap it all up by figuring out, how do you pick the right tool for the job? Okay, first things first, the leveling challenge. See, the real goal here isn't just knowing the level. It's about automatically doing something with that info. Taking human error completely out of the picture. And this right here, this is the solution in a nutshell. It's a really simple, kind of elegant loop. You've got the level sensor, which is basically the eyes. It sees the liquid. It shoots that information over to a controller, which acts as the brain. The controller thinks, makes a decision, and then tells the pump, that's the muscle, to either kick on or shut off. It's that simple. See, think, act. I mean, that's automation at its most basic. Now, it's important to know that not all sensors see things the same way. The biggest difference, really the most fundamental one, comes down to two main approaches, what we call point level and continuous level measurement. So here's what that actually looks like. Over on the left, you've got point level measurement. The best way to think about these are as, well, tripwires. You put one near the top to scream, hey, we're full, and maybe another one down at the bottom to warn, whoa, we're getting empty. But on the right, you have continuous measurement. That's a lot more like the fuel gauge in your car. It's giving you the exact level all the time. So what it all boils down to is the question each one answers. A point level sensor gives you a dead simple binary answer, yes or no. Is the liquid right here at this spot? That's it. A continuous sensor, on the other hand, gives you an analog answer, a precise value like 7 feet, 52% full, or 10,000 gallons remaining. Okay, so let's zoom in on those specialists, the point level sensors. These things are the absolute workhorses for your basic high and low level alarms and simple pump controls. So here you can see the whole family. You've got float switches, capacitance sensors, conductivity probes, and those tuning forks. They all look different, but they share one key thing in common. They all act like a simple light switch. They send a basic digital on or off signal, a 0 or a 1, back to the controller. Let's kick things off with probably the most intuitive one of the bunch, the float level switch. The concept is ancient, right? I mean, we're talking Archimedes level simple. You've got something that floats, and you just use its movement to trigger a switch. And you can see that exact principle in action right here. As the liquid level comes up, it lifts the float. That physical movement is directly connected to a switch inside, which then closes an electrical circuit. It's just beautifully simple. And for a lot of jobs, incredibly effective. But, of course, that elegant simplicity comes with trade-offs. On the plus side, they're often non-powered and really inexpensive, which is awesome for simple jobs. The big downside, though, is that they have moving parts. And moving parts can wear out, they can get stuck, which makes them not so great for, say, corrosive liquids or for systems where a single failure would be a disaster. All right, next up, we've got a sensor that works on a totally different principle, the capacitance level switch. Now, this one is pretty cool. It uses electrical properties to figure out the level. So, how in the world does it do that? Well, think of it like this. The sensor's probe and the metal wall of the tank act like the two plates of a capacitor. And whatever is inside the tank, air, liquid, whatever, that's the stuff in between. Now, since liquid and air have different electrical properties, a tank filled with liquid has a higher capacitance than an empty one. So the switch is just sitting there waiting for that capacitance value to hit a certain level, and then, bam, it triggers. So you get some pretty big wins with this design. They're small, they're accurate, and, this is a big one, no moving parts to break. They can even work with both liquids and solids. But, and there's always a but, the trade-off for all that solid-state goodness is the setup. You have to carefully calibrate them for whatever material you're measuring, and they're definitely not a one-size-fits-all solution for every substance out there. All right, Let's move on to our next specialist, the conductivity level sensor. This one's even more direct in its approach. It basically just asks the liquid one simple question: hey, are you conductive? And this visualizes the principle perfectly. You've got two electrodes just hanging out. In an empty tank, nothing's happening. It's an open circuit. But the second a conductive liquid, like water, comes up and touches both of them, zap! It completes the circuit. A current flows, and the sensor sends out its signal. For the right job, these sensors are a fantastic trade-off. I mean, no moving parts, super low cost, easy to use. They seem perfect, right? But here is the big, non-negotiable catch. The liquid absolutely has to be conductive. That means they're totally useless for things like oils or even highly purified water. And another thing to keep in mind, that probe is always in the liquid, with a current running through it, so yeah, it's going to erode over time. Okay, our last specialist in the point level category is the vibrating switch. But you'll almost always hear it called a tuning fork. And this one is built on a really, really clever idea that's all about vibration and frequency. So here's the really clever part. The two prongs on the fork are always vibrating at a very specific frequency in the open air, just like a musical tuning fork. That frequency is constant. But the moment those prongs get covered by a liquid or even a solid, it dampens the vibration and that frequency changes. The electronics inside are just listening for that tiny shift, and when they hear it, they trigger the switch. It is so darn reliable that you see these things everywhere, in mining, food industries, chemical plants, you name it. All right, so we've covered all the specialists, but what happens when a simple yes or no just doesn't cut it? What if you need to know the whole story? Well, that's where continuous level sensors come into play. And these represent the next big leap. Unlike everything we've talked about so far, these are often non-contact, which is a massive advantage. You've got technologies like ultrasonic sensors, which send a pulse of high-frequency sound down to the surface of the liquid. And then you have radar, which does the same thing, but with a microwave pulse. In both cases, the sensor is just measuring the time of flight, basically how long it takes for the echo of that signal to bounce back. A longer delay means a lower level in the tank. This gives you a super precise, continuous measurement that tells the control system the full picture, not just a simple on or off. Whew, okay, we have covered a ton of ground. We started with all those point level specialists, the simple mechanical floats, the electrical capacitance and conductivity probes, and those super reliable vibrating forks. Then we jumped to the big guns, continuous measurement tech, like ultrasonic and radar, that give you the whole story. So all of this brings us to the final and most critical question. With all these options on the table, how on earth do you choose the right one? Well, the truth is, the choice depends on, well, everything. Is the liquid corrosive? Is it conductive? Does it get foamy? Do you just need a simple on-off alarm, or do you need pinpoint accurate inventory management? Think about it. Every single substance we rely on, from the milk in your fridge to the fuel in a rocket, has to be measured somehow. So now that you know the tools of the trade, which one would you pick for the job?